So a precipitate, an example of a precipitate, let me show you a video here. Here we'll watch a precipitate form when we combine these two solutions. So they're solutions, again. A solution means a solvent. The solvent in both of these scenarios is water. A solution is a solvent with something dissolved in it. All right, so there's a salt, like sodium chloride. Now remember, the term salt just means any ionic compound. So we have an ionic compound in here dissolved. We have a different ionic compound in here dissolved. And remember, when an ionic compound is a solid, it comes in a three-dimensional lattice, but then when you put it into water, all the ions spread out amongst the water molecules and separate from each other. And that's what dissolving or dissociating means. Okay? So what we're going to do is we're going to combine these two together. And when we do, we're going to see a powder form. Now, it looked kind of like who knows which one I think that is, kind of like a liquid or something. But when you have a solution like this that you can't see through because there's something cloudy in it, that's little particulates, little pieces of powder, and that's a solid, and that's what we call a precipitate. Okay? So, in this type of an equation, we have silver nitrate. It's the solid, but it's been dissolved in water, and that's what that aqueous sign means. And we're adding potassium chloride. It's a solid as well, but it's dissolved in water, aqueous. And the result is silver chloride, which is a solid, which means it can't dissolve in water, so it crashes out like that precipitate that we just saw did. Okay? And then we have the other product forming, which is potassium nitrate. And potassium nitrate is soluble in water, and so it stays in the aqueous form. All right, so we have chemical reactions like this. And if you can see here that these chemical reactions follow kind of a pattern, right? You have an ionic compound, right? So here is where we start. We have an ionic compound, and we'll say that in that ionic compound we have A, where A is some sort of a cation, and B, where B is an anion. So the cation here, can you see what the cation is? It's the silver ion. And the anion, which is the negatively charged, is the nitrate. And we can see that on our back of our periodic table, right? Every time we come across one that we don't know, we have to look it up. So it's a nitrate ion, NO3 minus. Okay? So this ionic compound, AB, cation, anion, is combining with another ionic compound, CD, anion, cation. And the result is this A, anion, goes with, cation, anion. This cation goes with that anion, AD. And this cation, C, goes with B. So we have C going with B. Can you see that up here? Our A, B, C, D, and then A with our D, and C with the B. Okay? So this ABCD model here, right, is one that you can identify pretty easily by looking at an equation like this. And usually these types of reactions occur because one of the products is insoluble, which means it's a precipitate, which is solid when it's formed. All right? Now, in this chemical reaction, there's a little more occurring, and we want to become familiar with it and make sure you understand what's going on in this specific reaction. So we break this chemical reaction up into what we call an ionic equation. And the ionic equation is just taking these ionic compounds and breaking them up into the ions that they form when they're put into solution. Just like before, we were taking the ionic compounds, breaking them up into ions. Here we're doing the same thing, breaking these up into ions. Now the silver chloride, which is a solid, doesn't break up into ions. It stays together, and so we keep it together. But everything else we break up into ions. This is called the ionic equation. The ionic equation. We've taken our ionic compounds, and those that are aqueous break up into ions. Solid means it was the precipitate. It won't dissolve in water anymore, and so it's there like that. This is our ionic equation. We can get our net ionic equation when we look to the left and to the right and see the things that didn't change. So over here you see the nitrate ion and the potassium ion. They didn't do anything. They didn't undergo any chemical reaction. And so we can remove them. Those are called what we call spectator ions. We can remove them from the equation. And what's left then is the net ionic equation. It's the chemistry that actually occurred. So in this reaction, the silver ion found the chloride ion and formed an ionic compound that is not soluble in water, won't dissolve, so it is a precipitate. So we write an ionic equation by looking at the original equation, breaking up things that can break up, that are aqueous, right? Separating out those ions, make sure we have the same number of ions, and then we can go further to the net ionic equation, and by eliminating any spectator ions, crossing out any spectator ions. Okay, so we'll do the first one together, and then you'll work on the second one. So we're going to write the ionic equation for this reaction. Okay, you start off with BaCl2, barium chloride, whoops. Oh, let me start over. Barium chloride, lead nitrate, and this is lead 2 nitrate. Can you see that? Because the nitrate ion has a -1 charge, right? All right. So, and they tell us that the products are lead 2 chloride. That's a solid. Let's put that in there to emphasize that, because that is how we know, right? I didn't write aqueous on all of these, but we can see it up there. But because this is a solid, when we write our ionic equation, we don't break up the, the solid here. So now we break this into ions, and remember, I have the barium ion and the chloride ion. The 2 there is indicating that I have 2 chloride ions. There's a negative charge on the chloride ion. The barium ion, if I don't remember what kind of charge there is on the barium ion, I can look it up on my periodic table. But in general, let me bring my periodic table over here, right? The periodic table, barium, right here, right, has a +2 charge. Okay, so let me lost my thing here. Let me bring all this stuff back. Where is the other one? This one here. Okay, so the barium has a +2 charge. All right, we break this up into ions like before as well. There's one lead ion, Pb. What's the charge on it? Well, I look on my periodic table on the back, and I find out what the charge is on the nitrate again. Right? I see that the charge on the nitrate is a -1. So that means that the lead must be a +2 because there's 2 of these nitrates. So I go NO3 -1. I remember, though, that I have 2 of them, so I have to put a 2 in front there. Okay? And then the product here, solid, doesn't get broken up into its ions in the ionic equation. Whoops, PbCl2. So I just keep that together. This is aqueous. Again, I see up here that it has an aqueous sign. Right? So I break that up into its ions. 1 barium, +2 charge. Again, the periodic table tells me that. 2 of these nitrates, NO3 minus 2 of these nitrates. Okay, so that is my ionic equation. That's my ionic equation. All right? So, why don't you go ahead and identify the ionic equation for this second one? Okay, so go ahead and get the ionic equation for this second one. And after you're done, we'll show it to you. Now push pause so you can take a second to look at it. Okay, so hopefully you took time to do it. Don't just skip ahead. Make sure you take time to do it. Let's see if you got it right. All right, so look at all the different coefficients, right? 2. Make sure you have your charges right. Okay, make sure you didn't separate this one because it was a solid. 2 here, plus 1, 2, Cl minus, not Cl with a 2 down here. All right, so everything has to be exactly right there. All right, so that's the net ionic equation for that one. All right, now, sorry, that's the ionic equation. Now, if we want to write the net ionic equation, we do the same thing. We get our equation, and then we go to the ionic equation, and then we just cancel out the spectator ions. It's the spectator ions that are taken out of the ionic equation to give us the net ionic equation. So, for example, in this one here, the first ionic equation that they provide for us, we can see the spectators because they don't change from left to right. So we have 2 nitrate ions that don't do anything, right? They're the same as on both sides of the reaction. So those ones will be canceled out, along with these potassium ones that don't change as well. All right? And then the net ionic equation is what's left. All right, so for these next 2 here, why don't you find the spectator ions, cross them out, and then write the resulting net ionic equation. Take a few minutes to do it right. So push pause now, take a few minutes, and then do it. Okay, hopefully you're finished. And let's see how you did. All right, so that's pretty straightforward, right? We're just crossing out the spectator ions, the ones that are watching, and there's no chemistry actually occurring on them. Okay? All right, good. So, here's another opportunity. Look here, see if you can figure out which one has the correct ionic equation. We're not looking for the net ionic equation here. Look at the differences between A, B, and C and try to find out why each one of them is wrong. Okay? Push pause. Take a minute to do this. All right, hope you push pause and took a minute to do that. Now, I'm going to show you the answer. All right, good. So you can see that the first one has problems, right? A has problems. This isn't what a chloride ion looks like. A chloride ion is a Cl minus, not a Cl2 with 2 minus like that, right? C has problems as well because it broke apart the barium sulfate. The barium sulfate here is a solid. It's the precipitate, so it doesn't break apart into its ions. Solids, if you put something into water, that's an ionic equation, and it doesn't break apart, then it won't dissolve. It'll just stay solid. All right. So, up till now, we've talked about compounds that, ionic compounds, that when they're placed in water, they ionize, right? So, again, let me give you an example here. Sodium chloride, solid, right? That's salt. That's like table salt, right? If I take that and I put it into, let me see if I can push this the other way. There we go. Give me a little percent. I put this into a water, put sodium chloride into water. What happens is, again, the sodium ions separate from the chloride ions and they dissolve, dissociate. All right? We've talked about that. If I take a compound like this one as an example, put it into water, so maybe this is a gas or solid, put it into water. So I can put like water up on top to show that I'm putting it into water. Well, we would get PCl3 aqueous, but it won't ionize. Why won't this one ionize? See how this one ionizes into its ions, or another word for that is dissociates. Why doesn't this dissociate? It does dissolve, but it doesn't dissociate. Why is that? See if you can answer that question. Why doesn't PCl3 dissociate the way NaCl does? Push pause, think about it, and then when you're done, we'll answer the question. So, ready for the answer? The answer is because PCl3 is a molecular compound, right? If you look at our phosphorus here and Cl3, those are nonmetals to the right of the staircase. So it's an ionic compound, and it's not going to be forming it's not going to be releasing ions, right? But there are some molecular compounds that when you put into water, they actually do dissociate like this. Now, it's very few number of them, and they get a special name. Another thing that's special about them is that all of them contain a hydrogen ion. So an example of one of these is this compound, HCl. If you look at our periodic table again, we'll see that hydrogen, which is a nonmetal, chlorine, a nonmetal. So this is a molecular compound, right? So it's a molecular compound, but when we put it into water, it dissociates into ions, H plus ion and Cl minus ion. Okay? Another example is this compound, HC2H3O2. You put it into water, and an H plus ion results, and the C2H3O2 minus ion. Look for the name of that ion on your paper. I'll give you a second to find it. Did you find out what it was? It's the acetate ion, right? Acetate ion. So this goes into solution, and you get the hydrogen ion and the acetate ion. All right, so some molecular compounds will actually, when placed in water, dissociate into, and I'll put aqueous on all of these so you can see that these are now dissolved in water, into their ions. Okay, so what this is showing is that this group of compounds that are molecular dissociate, and these group of compounds we call acids. Acids. Now, you've heard of the word acid before. An acid, maybe in the past you've heard about acids being compounds that release a hydrogen ion, right? And that's true. You put them into water and a hydrogen ion results. Acids are always also molecular compounds. Molecular compounds. All right? So molecular compounds that dissociate when placed into water or ionized like this also always contain a hydrogen ion. Hydrogen ion. So you can usually tell an acid because it begins with a hydrogen ion, like HBr, for example. This is an acid. They help us by usually starting the compound with a hydrogen ion. Okay, so here's another one, HClO4. All right, so that acid, HClO4, starts with a hydrogen ion. To write its dissociation, right, one of the ions is always H plus, and the other one is always whatever is left with a minus charge. Okay, so for this one, hydrogen ion, and whatever is left is always having a negative charge. Okay, or at least a one more negative charge than it was previously. All right, so this is how we write the dissociation of an acid. An acid. Okay, and we call these Arrhenius acids. Okay, acids that release hydrogen ions. All right, we also can differentiate between what we call strong and weak acids. Strong and weak acids. HBr is an example of a strong acid, whereas this acid, which we call acetic acid, also known as vinegar is a solution of acetic acid, is a weak acid. Weak acids we draw with an arrow going backwards because, yes, they dissociate, but as soon as they dissociate, they try to come back together and go back to this. So at any given point, there's a very small amount of this acid actually dissociated. Strong acids, on the other hand, so this is our strong acids, an example of our strong acids. I'll write weak here. Strong acids, on the other hand, you put them in water and they completely dissociate and they stay dissociated. This is called perchloric acid. It is also a strong acid. Okay? So, let's see, we're not going to talk about non-metal hydroxides, but we will talk about bases now. So you've heard of acids, and you probably also have heard of bases. And a base is the opposite of an acid, all right? Or in other words, an acid is a chemical. A generic acid looks something like this. HA, the chemical starts with a hydrogen, has something else. You put it into water, H plus results, and then the other thing with a minus charge, whatever is what we call the counter ion, the ion on the other side of the H plus ion, right? Okay, that's the general definition or general example of an acid. A base is the same type of thing. You put it into water, but instead of resulting in the hydrogen ion, you result in the hydroxide ion. So an example is sodium hydroxide. Sodium hydroxide is an ionic compound. Bases aren't necessarily molecular compounds only. Bases can be ionic or molecular. Here it's an ionic compound. You put it into water, and because of the dissociation, you end up getting the hydroxide ion. So acids compounds that result in H plus when placed in water, and bases, compounds that result in OH minus when placed in water. Okay? Now, on the slide here, there's an interesting example of a base, right? It's NH3. Now this is, if you look at our periodic table, and we see that this is a molecular compound, nitrogen and hydrogen. So it's not going to ionize. So how in the world is it going to release a hydroxide ion? Well, some bases, they don't release a hydroxide ion themselves, but they interact with water, and they take a hydrogen ion and leave behind the hydroxide ion. So if you think about a molecule of water, here's a molecule of water, H2O, right? An H plus ion is part of this molecule, and the OH minus ion can be the other part. So acid is when a compound releases this part of the molecule, of a water molecule, just an H plus, and a base is when it releases that part. All right, so those are our definitions for acids and bases. Okay, so here's some examples again of ionic compounds behaving like bases, right? Magnesium hydroxide, you put it into water, it dissociates into magnesium ion and hydroxide ion. And then there's also examples of, let's move forward here, to compounds behaving as bases that are molecular. So NH3, the one we just drew, interacting with water, it makes the NH4 ion, and then it releases the hydroxide ion. And that's how you see that it is behaving as a base. Because, again, the definition of a base is a compound that results in the hydroxide ion when it's placed in water. All right, so again, strong versus weak. Strong acids or strong bases completely dissociate. And we have here 6, 1, 2, 3, 4, 5, 6. There's 7 strong acids. So we forgot we don't have HClO3. I mean, different books do different things, but we're going to, in this class, use 7 strong acids. And these strong acids are ones that you'll want to begin to memorize, okay? And I'm sorry, but there's no other way to go about doing this. You're going to have to gradually remember and memorize these strong acids. All right? This is hydrochloric acid. HBr and HI. These are hydrochloric hydrobromic acid, hydroiodic acid. Okay, that's 3 of our strong acids. HNO3 is called nitric acid. H2SO4, sulfuric acid. All right. HClO4, perchloric acid. Whoops. Perchloric acid. And then HClO3 is just chloric acid. So those are our 7 strong acids. All right? And everything else we say is a weak acid. A weak acid. Okay? Very good. Now, there are strong bases as well, but we'll remember them a different way. So you don't have to be too concerned about that right now. All right. Well, I think that's a good enough time for now. Hopefully you went through that as slow as necessary. You answered the questions as necessary so that you didn't feel like you were missing too much. And hopefully that you learned a little bit. And if you fell asleep, rewind it and watch the different parts again. Okay, I'll see you guys on Monday.